Hi, and welcome to Dr. B's AP Chemistry webcast. In this webcast, we're going to be discussing the periodic trends for ionization energy. So what are we going to talk about in this webcast? Well, first we need to define ionization energy. You need to know what it is. And then we're going to state the period and group trends for ionization energies and explain these trends in terms of Coulomb's law, which is a really important emphasis in AP Chemistry. And of course, we're going to do practice problems that are AP Chemistry style. Let's say we have a neutral, isolated gas phase atom, and then this atom is bombarded with some energy. What's going to happen is that we're going to be left with a cation because an electron will be kicked off. So when we talk about ionization energy, we're talking about the energy that I have to put into the atom to remove an electron. Specifically, it's the energy required to move the outermost electron from an isolated gas phase atom. Now we can also represent this in an equation form, A being the atom plus the IE makes a cation of A plus an electron. Notice that the ionization energy term is written with the reactants. That means this is always going to be an endothermic process, and the values for ionization energy are always going to be considered positive values relative to the atom. In this graphic, we've got ionization energy data for a large collection of main block elements, and there are some very clear patterns here. Let's talk about the period trend. As we go from left to right across the period, it's very clear to see that the ionization energy increases. We see this pattern again and again and again. It's important that you know the trend, that ionization energy increases from left to right across the period. But what's even more important is that you're able to explain why. What's happening is that you're adding electrons to the same energy level. So the atom on the left is an atom of lithium, and it's got one electron in its 2s sublevel, in energy level 2. Beryllium is the atom on the right, and it's got 2 electrons in the 2s sublevel in energy level 2. The electron-electron repulsions are really the same. So what's the difference here? Why are we seeing this increase in ionization energy? Why does it take more energy to remove an electron from beryllium? An atom of lithium has 3 protons in the nucleus, so it's got a nuclear charge of +3. An atom of beryllium has 4 protons, so it's got a nuclear charge of +4, and that's really the key difference. The nuclear charge, the number of protons, is increasing from left to right, but we're adding electrons to the same energy level. Therefore, as the nuclear charge increases as we go from left to right, the outermost electrons experience a stronger Coulombic attraction to the nucleus. Therefore, as we go from lithium to beryllium, the outermost electrons of beryllium are held more tightly than the outermost electrons of lithium. So let's look at this from a slightly different perspective, a slightly different visual. Here's my lithium atom. I've got 3 protons. I've got my 3 electrons, 2 electrons in energy level 1, 1 electron in energy level 2. And there's a certain Coulombic attraction between that electron in energy level 2 and the 3 protons. But when I look at beryllium, I have 2 electrons in energy level 1 and 2 electrons in energy level 2, but I have 4 protons. And so the Coulombic attraction between the electrons in energy level 2 of beryllium to the 4 protons in the nucleus is a stronger Coulombic attraction, and that's the heart of this explanation. The outermost electrons in beryllium experience a stronger Coulombic attraction to the nucleus than the outermost electrons of lithium, and that's why ionization energy increases as we go from lithium to beryllium. And we see this pattern from left to right, and the explanation is always the same. As the nuclear charge increases, the outermost electrons experience a stronger Coulombic attraction to the nucleus. So the outermost electron of lithium in the 2s sublevel is not as strongly attracted to the nucleus as the outermost electrons of beryllium in the 2s sublevel to the nucleus of beryllium. And therefore, more energy is required to remove the outermost electron from beryllium than it takes to remove the outermost electron from lithium. Now, if you look at the data, the trend is not perfect. There are some discrepancies in the trend, and AP Chemistry students should be able to discuss these. So there's a discrepancy between groups 2 and 13. We're not really paying attention to the transition metals here. But we do see this discrepancy between beryllium and boron, between magnesium and aluminum, where the trend doesn't quite hold. Why does this happen? Let's compare the structures of beryllium and boron, because that's really how we're going to answer this question. If we look at beryllium, it's got the electron configuration 1s2, 2s2, which we were just looking at several times. Boron has the electron configuration 1s2, 2s2, 2p1. An electron in a 2p sublevel is farther away from the nucleus than the electrons in the 2s sublevel. Now, it's not a huge difference, but it is a little farther away. And therefore, the outermost electron of boron in that 2p sublevel experiences a weaker coulombic attraction to the nucleus than the valence electrons of beryllium in their 2s sublevel. And so we see this discrepancy. So these kinds of discrepancies can often be explained by looking at the electron configurations of the two elements. If you look closely at the period trend again, we see that there's another discrepancy between groups 15 and 16. Now, it's a fairly small discrepancy, but it is there for several periods. The ionization energy of nitrogen is larger than the ionization energy of oxygen. The ionization energy of phosphorus is larger than the ionization energy of sulfur. Why is this? Again, to explain these discrepancies, we're going to look at the electron configurations of nitrogen and oxygen. Nitrogen's electron configuration is 1s2, 2s2, 2p3. Oxygen is 1s2, 2s2, 2p4. And this is really the key. But until we look at arrows and boxes at orbital configuration, it's not going to be clear. So if we look at arrows and boxes for nitrogen, we see that we have 3 half-filled orbitals in the 2p sublevel, right? We have 3 2p orbitals that are half occupied, 1 electron in each. And they're all spin aligned, of course, because we're following Hund's rule. But having this minimizes repulsions. But let's look at the electron configuration of oxygen. We have 4 electrons to go into that 2p sublevel. And so when we write the electron configuration of oxygen using arrows and boxes, we don't have 3 half-filled p orbitals like we did in nitrogen. Only 2 of them are half-filled. 1 of them has to be fully filled. So now we have more electron-electron repulsions between those p electrons. So what we see is that the 2p electrons of oxygen are going to experience more electron-electron repulsions than the 2p electrons of nitrogen. And that's why the first ionization energy of oxygen is less than the first ionization energy of nitrogen. It's going to take less energy to remove a 2p electron from oxygen than from nitrogen because I've got more electron-electron repulsions, which means those electrons are held a little less tightly. Now let's think about the group trend for ionization energies. As we go down a column, ionization energies get smaller. That's our typical pattern. Ionization energy decreases as we go down a column. And you need to know that trend. And you need to know why. We're going to use alkali metals to discuss this. The main structural difference as we go down a column is that the atoms have more occupied shells. They have more occupied energy levels. The electrons are going to energy levels that are farther away from the nucleus, and that's the key. Let's start with lithium. We know it's 1s2, 2s1. Its highest occupied energy level is energy level 2. So we can diagram that, 2 occupied levels, and our valence electron is in energy level 2. If we think about sodium, its last electron is in energy level 3. So we have 3 shells that are occupied. So its valence electron is in energy level 3. And if we then look at potassium, its outermost electron is in energy level 4. And so the energy levels, of course, are inherently farther away from the nucleus as we add more energy levels. That really is the critical component to explaining this trend. Electrons are occupying higher energy levels that are farther from the nucleus. And if they're farther from the nucleus, if the distance is greater, the coulombic attraction to the nucleus is smaller. And so as we go from lithium to sodium to potassium, the outermost electrons are experiencing a weaker coulombic attraction to the nucleus because they're farther away. So here's the big picture. As the distance between the valence electron and the nucleus increases, because we're adding additional shells, the coulombic attraction between the valence electron and the nucleus decreases. Now we are going to go and do some practice problems, but before I do that, I wanted to discuss test-taking tips, especially if you're doing free response questions about periodic trends. You need to remember that restating the trend is not considered an explanation. You can restate the trend if you want to, but that by itself is not sufficient. Make sure you specify which species you're talking about. Write the name, write the symbol. Don't write it, because we don't know what it is, especially if the problem asks you to compare 2 different atoms or 2 different ions or 2 different species. Be very, very clear in your answer. Make sure both elements are included in your answer. If your question is asking you to compare 2 atoms and their trend, make sure you have both of them in your answer. And you really need to focus on Coulomb's law in your response. What's the effect of the changing nuclear charge if you're going from left to right across the period? What's the effect of increasing distance if you're adding more energy levels? That's really what the focus of your answer needs to be. So let's work through practice problem number 1. The table below shows the first ionization energies for sodium and magnesium. When I'm talking about first ionization energies, I mean the energy to remove the valence electron from a neutral atom. We're giving you the data. This is actually a very typical thing in AP chemistry questions, where we give you data to show you the trend. What's the question then? The question is, explain why the first ionization energy for magnesium is greater than the first ionization energy for sodium. Refer to principles of atomic structure in your answer. And what I really want? Coulomb's law. So let's work through this. The trend is clear. As we go from sodium to magnesium, the ionization energy goes up. Both elements are in period 2, and both of them have valence electrons in the 2s sublevel. So it's not a sublevel issue. What's the main difference? Well, as we go from sodium to magnesium, we see that sodium has 11 protons, magnesium has 12 protons. The outermost electrons are in the same sublevel. The difference is the nuclear charge. The outermost electrons of magnesium experience a greater Coulombic attraction to the nucleus than the valence electrons of sodium experience, and that's our answer. That's really the heart of it. And therefore, it takes more energy to remove a valence electron from magnesium than it takes to remove a valence electron from sodium. Notice I've got both species in here. I'm comparing them very specifically. I'm specifically comparing the nuclear charge. You want to make sure your answer is thorough and complete. Let's look at practice problem number 2. It's a very similar sort of setup. The table below shows the first ionization energies for carbon and silicon. Explain why the first ionization energy for carbon is greater than the first ionization energy for silicon. Again, refer to principles of atomic structure in your answer. We see that both elements are in group 14, and we know both of them have 4 valence electrons. What's really important, though, is where are the outermost electrons? In carbon, the outermost electrons are in energy level 2, in that 2p sublevel. And for silicon, the outermost electrons are in energy level 3, in that 3p sublevel. But energy level 3 is farther away from the nucleus than energy level 2. So the outermost electrons of carbon are at an energy level that is inherently closer to the nucleus than the outermost electrons of silicon. And therefore, the 2p electrons of carbon, our valence electrons, experience a greater Coulombic attraction to the nucleus than the 3p electrons of silicon experience in terms of a Coulombic attraction to the nucleus. And therefore, it takes more energy to remove a valence electron from carbon than it does from silicon. So we're given the trend, we need to explain it. I'd like to wrap up with a summary of key points that we talked about. Ionization energy increases as you go from left to right across the period. Ionization energy decreases as you go down a column. We can explain both of these trends using Coulomb's law. We're looking at changes in nuclear charge. We're looking at changes in distance from the nucleus. Subscribe to my channel so you get all my latest videos. Like the video, leave a comment, and practice chemistry every day. That's how you get better.